Good morning, everyone. Welcome to Lecture 3. Before I get started, I forgot to mention something in the last lecture that I'll mention now. Just to make things easier on you, I'm going to post my PowerPoint slides so that you can take notes using the PowerPoint slides, like directly on the PowerPoint slides, while you're watching the lecture videos. I think that might actually make it easier for you to take notes because I can talk kind of fast and sometimes I ramble. Anyway, so let's get started with Lecture 3. All right, so in this lecture, we're starting to get into the the, the gist of chemistry, my favorite parts of chemistry, and that is chemical bonds. Right. So there are a couple types of different chemical bonds, right? And those two types of chemical bonds are ionic bonds and covalent bonds. Covalent bonds are usually between nonmetals, and it's a sharing of electrons is what you need to remember about that. Whereas ionic bonds are a transfer of electrons, right? They're a transfer of electrons. So all this is predicated on the octet rule, where I was talking about before in the last lecture. The octet is 8 valence electrons in the outer shell, right? So in the example of an ionic bond that we have over here, we have a metal, right? And again, if I didn't already say this, ionic bonds are usually between metals and nonmetals, and it involves a transfer of electrons, right? You have a nonmetal over here that only has 7 electrons in its outer shell, making it one, missing one in its outer shell. It only needs one more to get a full outer shell, so the metal could come over and transfer one of its electrons to the nonmetal, and then the nonmetal will have 8 in its outer shell. But then you're asking yourself, why is the metal going to do that? I mean, does it need to have an extra shell too, or a full shell too? Well, it turns out that this particular metal here only had one electron in its valence shell or outer shell, and since it transferred that electron to the nonmetal, its now outer shell, which you don't see, is full, right? So when that happens, the metal becomes a positive charge, and the nonmetal becomes negatively charged, right? So that's the hallmark of ionic bonds. In covalent bonds, of course, like I was saying before, two nonmetals together, and they actually share electrons. In this case, this nonmetal here has 7 electrons. Same with this one here, 7 electrons. And instead of transferring an electron from one to each other, they just share an electron, making a bond, making a covalent bond, right? And they share those electrons. And when this occurs, there's no change in charge, right? There's no charge. They're neutral, right? They're neutral because they're sharing electrons. So, big thing to remember: octet rule, 8 valence electrons, and then ionic bonds are between metals and nonmetals, right? And it's a transfer of electrons from one atom to another. A covalent bond is between two nonmetals, right? And they share their valence electrons to achieve the octet rule of 8. All right. So let's take a closer look, a deeper dive into ionic bonds. Um, so let's use, for example, sodium as an example. Here we have sodium metal. If you recall what I said to you before, sodium metal, right, is an alkali metal, right, and it has an ionization energy that makes it very conducive to wanting to be reactive with the vapor in water, right? And why is that? Well, the reason why that is because sodium has this, excuse me, has this one extra electron just kind of floating around, right? And that electron just needs to go somewhere. It really does. Okay, and so with that extra electron right there, that sodium metal, even though it's neutral right now, it has an extra electron just sitting there. And the important thing to remember that even though it's important for an atom to be neutral, it's actually more important for the atom to have 8 electrons in its outer shell, or a full outer shell, right? A full outer shell. Um, I say full instead of 8 because there are some electrons that have, or some atoms that have less than 8, right, electrons total, and they have full outer shells in the way of, for example, helium, which has 2 electrons. The first shell only has 2 electron spots, right? And so technically helium has got a full outer shell. So it's actually more important for an atom to have a full outer shell than it is for it to be neutral. So in the case of sodium here, it's got that extra electron just kind of hanging around. It needs to go somewhere. Um, but then you have chlorine gas, right? Chlorine gas actually has an extra, has 7 electrons, right? 7 electrons in its outer shell. It just needs 1 electron to uh, it just needs 1 electron to be to have a full outer shell. So kill 2 birds with 1 stone. You transfer 1 electron from sodium, right, to chlorine, and then sodium now has a plus charge. But even though it has a plus charge, it now has 10 electrons, which means there's 2 in the first shell, and then in the outer shell there's 8, giving it its octet that it's always wanted, instead of that extra electron just floating around. And then that extra electron that sodium just lost, it transferred over to chlorine, right? So now chlorine has excuse me, now chlorine has a full outer shell because it had its 2. Let me just put in their symbols here so we don't get confused. Now it has its 2, right, that are here. I'm sorry, I should have drawn these electrons together. They're not like spread apart the way that way. There we go. There's 2 electrons for chlorine's innermost shell, and then 8 here in its second shell, right? That makes 10 electrons, but since it had got an electron transferred over from sodium, instead of having 17 electrons, it actually has 18 electrons now. So that's 10 total so far, and now you have chlorine has its 8 in its outer shell. Let me shut off my face so you can actually see what I drew. There we go. So now chlorine has 8 in its outermost shell, the third shell, right? And since it has an extra electron, even though it's got a negative charge now, right? It's got a negative charge. It is much happier with a full octet in its outer shell, right? Same thing with sodium. It lost that one that used to be in its outermost shell, the third shell, and it gave it over to chlorine. And so now its outermost shell has a full octet. So when it's all said and done, we have sodium with a plus charge because it lost an electron, and then chlorine with a minus charge because it gained an electron, right? Now they're not neutral charge anymore, but they're happy because they have both full outer electron shells, and you end up getting the compound NaCl, which is just common table salt, right? Which is this right here, right? So that's the basis of ionic bonds. Let me bring myself back now. And we can, before we move on to the next slide, just so you know, ionic bonds are actually very strong, right? And you already saw that they're between positive and negative ions. Oh, by the way, I forgot to say that. This, whenever the electrons whenever sodium loses an electron, and it becomes this negative charge, it becomes a positive charge because it lost an electron, right? This is called a cation. Oops. Let's write that again. Cation, right? Or a positively charged ion. Yeah, positively charged ion, right? That's just nothing. A positively charged ion. And in the case of chloride, which is the chlorine ion, right? It gained an electron from what used to be neutral, so we call this the anion, or the negatively charged ion. Sorry, what's happening here? There we go, the negatively charged ion, right? So now that we've seen sodium chloride or table salt or NaCl as an ionic formula, let's talk about in general how to write ionic formulas. Recall that I previously stated that metals are normally positively charged in an ionic formula, so we call that a cation. And then nonmetals are negatively charged in ionic compounds, and we call that an anion, right? Those are anions. So ionic formulas or ionic compounds are composed of a cation and an anion, right? So let's see here. Let's do a quick example here. For example, we can do magnesium, Mg, right? Mg is here in group 2. And since it's in group 2, it's got a +2 charge, or 2 plus charge, right? Over there, we were just talking about sodium in the previous slide. It's in group 1, so it has a +1 charge, right? But here we have magnesium, it's got a +2 charge. And what that means then is that magnesium needs to lose 2 electrons to obtain that full outer shell, valence shell, right? So it has 2 valence electrons. So the easiest way to do that is to find a anion over here, maybe at group 7, 7A, or group 17 right here, and we'll just use chloride or chlorine again, the anion for chloride, chloride, the anion for chlorine. Notice that it has a -1 charge, right? Which makes sense because when we were using it with sodium before over here, right? Sodium had a +1 charge, so you only needed 1 sodium to balance out 1 chloride ion, and it was neutral, and you made salt or NaCl. But it's a little different now with magnesium because magnesium has a 2 plus charge, right? And chlorine has a -1 charge. So you'll need 2 chlorines to balance out a single magnesium ion. So minus charge, minus charge. So one of these electrons goes to one chlorine, and the other electron goes to the other chlorine. So what you have then is Mg2+, and it's ionically bound to a Cl minus and another Cl minus. By the way, if I hadn't said it already, minus just means -1, right? And so that means then this molecule compound is called magnesium chloride. It's called magnesium chloride. And notice that when I write the formula, I have one magnesium for every two chlorines because I needed two negative charges from the two chlorides to balance out the 2 plus for magnesium. Alright, let's try that again. This time we'll use sodium. So sodium, excuse me, is in group 1, which we already talked about, and it has a +1 charge, right? Or or +1 charge, right? And so that means it has one valence electron. And we want to bind it to, say, sulfur. And sulfur is here in group 16 or 6A, and it has a -2 charge, which means that it needs 2 electrons transferred to it for it to become neutral. For it to become a full outer shell. So you need 2 sodiums, 2 sodium cations, right? And transfer one there, and transfer that electron there, right, to the sulfur. And then what you have left is sulfur with a -2 charge, and sodium with a +1 charge. So that gives us sodium 2 right there, because there's 2 sodiums, right? Sulfide with 1 sulfur. Sodium sulfide. Right? So the group number, for example here, group 1, corresponds to the number of valence electrons that all the ions in group 1 has. So for example, sodium is in group 1, so it has 1 valence electron, right? Therefore it wants to lose that, becoming +1, right? So that it can have a full shell in one of its lower electron shells, right? And the trend continues. Group 2 is the same way, right? Group 2 means that everything in group 2, for example, magnesium or calcium, right, has 2 valence electrons, which means it has 2 electrons it wants to get rid of so that it can have a full shell in a lower electron shell, right? Giving it a +2 charge when it loses those 2 electrons. And if we jump over to the anion side, or the nonmetal side, the group number corresponds to the valence electrons there as well, right? So group 7A, or group 7 I call it, for the purposes of this class, everything there, fluorine, chlorine, bromine, iodine, all have 7 electrons in their valence shell, or 7 valence electrons. Meaning that it needs to acquire 1 extra electron to become a full outer shell. And so when it does that, it becomes a -1 charge. Same thing over here with group 6, which is oxygen, sulfur. They have 6 valence electrons. They need 2 electrons for an outer shell that's full, right? When they gain those 2, they become a -2 charge, and that's where that charge comes from. The next group is group 5, right, over here, which includes phosphorus and nitrogen. 5 valence electrons means that it needs 3 electrons for an outer shell that's full, right? And when it gains those, it means it's going to have a -3 charge. So the periodic table, just by looking at where the ions are positioned on the periodic table, you can tell what the charges are, or how many valence electrons are available, right? Just so you know, though, there are some metals in this group here. These are the transition metals, and they have multiple charge states, right? Charge states. So, for example, chromium can be a +2 charge or a +3 charge. Manganese can be a +2 or +3. Iron can be +2 or +3. If you remember that from the very first lecture I gave with hemoglobin as the example, the iron in hemoglobin is without oxygen is a +2 iron, but when the oxygen binds to the iron, it becomes a +3 oxygen. So that's a very relevant example. Cobalt can be 2+ or 3+. Nickel can be 2+ or 3+. Copper can be 1+ or 2+. Silver is 1+, but gold here can be 1+ or 3+. So it can vary with the transition metals. The transition metals that we look at here, that are highlighted here, are the ones that we'll be using the most in this class to do ionic bonding. Transition metals, right? So let me clear this so that we can do a little bit of an example here. So let me do some examples now with the transition metals and naming these transition metals. It's not so hard with the other ones because you don't have to differentiate between different charges, but with like I was just saying, with the transition metals, they can have multiple charges, and so they have to be specified in their names. So let's say I had a formula like Mn, which is manganese, F2. How do I know what charge manganese is, right? How do I know what charge manganese is? Well, if I look over here at the fluoride, by the way, if I didn't already mention it, when a nonmetal becomes part of a ionic compound, for example here fluorine, when it becomes part of an ionic compound, it loses its ene and becomes fluoride, right? So that's fluoride there. Chlorine here becomes chloride. Bromine becomes bromide. And then iodine becomes iodide. And then oxygen becomes oxide. And then sulfur becomes sulfide, right? Nitrogen becomes nitride. And then phosphorus becomes phosphide. You don't have to do that with the metals, though. The metals will stay with their original name. So back to this, though. How do I know how to write the manganese name? Right? Because I don't know what charge manganese is. It could be a +2 or a +3 charge, right? But if I look over here at the fluoride ion, right, it has a -1 charge. So I need to have something that can match up with a charge in manganese that will match up with having two fluorides that are -1, which means combined it's -2, right? So the only thing that can balance out a -2 charge on the fluoride side is manganese 2+, right? And so the way I would write that is I would write out the name, the metal, manganese, and then the Roman numeral 2, and then fluoride. Because I want to balance out the charges of the anion with the charges of the cation, right? So let's try that again with another transition metal. Iron again. Iron it can either be iron 3 or iron 2, right? Or so iron 2 plus or iron 3 plus, right? So if I have something like FeCl2, this is super simple, right? Because we know that chlorine has a charge of -1. And so if I look at here, there's 2 chlorines, which means both of these together make a charge of -2. So that means to balance out that -2, this has to be a +2, right? So that's iron 2. So I write it out as iron 2 chloride. Iron 2 chloride. So there's some other names too, some other common names that we use in chemistry, especially as old folks, for iron. Instead of calling it iron 2, we could call it ferrous. Chloride. Right? Ferrous chloride. So ferrous, this suffix here, ferrous, it means the same thing as a 2 charge, right? If there's a 3 charge, so iron, whoops, write that again, iron 3 chloride, which has the formula Fe FeCl3. Sorry, had a little brain fart there. FeCl3, because this is going to be, that makes it a +3 charge to balance out 3 negatively charged chlorides, right? This is actually called ferric chloride. So ic in this case means 3, right? So either one of those is acceptable as answers. And as if you didn't think it was going to get any harder than that, because naming ionic compounds gets a little complicated, we also have the polyatomic ions too. And this is a list of all the polyatomic ions. Well, not all of them, but most of them that you're going to be responsible for. All right. Basically, polyatomic ions are groups of atoms with an overall charge, and they're often nonmetals that are combined with most nonmetals that are combined with oxygen. They're always going to have like a charge of 1, -1, -2, or -3, and except for the only one that doesn't kind of follow this rule is ammonium, right? Because it's ammonium is actually NH4 with a +1 charge, right? And it's not a nonmetal with a nonmetal with an oxygen, right? So things to remember about naming polyatomic anions, right? Polyatomic ions, and they're usually anions because they're negatively charged, is that most of them will end in 8, right? Like for example, NO3 -1 is an 8 nitrate, and then ClO4 -1 is chlorate, perchlorate, and then ClO3 -1 is also chlorate, and then CO3 -2 is carbonate, right? Or the acetate ion, which is what vinegar is made of when it's an acid, acetic acid, right? C2H3O2 -1, that also ends in 8 for acetate. Sulfate, SO4, 2- is also 8. So there's a lot of them there, right? So most of them are going to end in 8. So those are the common polyatomic ions, the ones that end in 8. But then if you have a related one, a related polyatomic ion that has 1 less oxygen, then the 8 becomes an ite, right? The 8 becomes an ite. So a good example of that would be nitrate here becomes nitrite, right? Because nitrate had 3 oxygens, and then nitrate had 3 oxygens, and the nitrite only has 2 oxygens, so it lost an oxygen, and that's why it becomes nitrite. And if you recall, back from my very first lecture, I was talking about how we can detect burned and unburned gunpowder, right? Well, unburned gunpowder is has the nitrate ion, right? The nitrate, which is NO3 minus. But once it gets burned, it loses an oxygen, right? And when it loses that oxygen, it becomes NO2 minus, right? Or NO2. And then its name is nitrite. Remember that? I used the modified Grice to do that detection when I was in the lab, right? You recall? There are other ones that are like that too. For example, ClO3, and ClO3 right here is the chlorate polyatomic ion, right? But if it loses an oxygen, it becomes ClO2 minus. It becomes a chlorite, right? We can actually take that even a step further too, because if it loses another oxygen, then it becomes hypochlorite, right? So ClO1 minus, and that means it only has 1 oxygen, as compared to the one above it, which had 2 oxygens, right? It's hypochlorite. Now, if you go the other direction, from chlorate, which is ClO3 minus, and it gains an oxygen, it becomes perchlorate, right? So the thing to know, remember about this, is that per, right here, generally means extra oxygen, right? And a good example of that would be like hydrogen peroxide. So water is H2O, right? But hydrogen peroxide is H2O2. So it's called peroxide because it has an extra oxygen, right? So same thing here. ClO3 minus has an extra oxygen, becoming ClO4 minus, and it's perchlorate. So that's what that per means, 1 extra oxygen than the normal. And then you can also think of it the other way here too, on the bottom end, where you lose an oxygen, where you only have 1 left, 1 oxygen, right? And hypo actually means below 1, right? Hypo, below. So let's see here, and then the other thing to notice about the polyatomics is that there are a couple that don't follow the rule, like these two, which we already talked about. Well, this one anyway, ammonium, right? So the ammonium is special because it's actually a +1 charge. It's like the only one that's not a negatively charged polyatomic, right? And so it doesn't have since it's positive charge, it doesn't have the 8 or ite or per or hypo things attached to it, right? So that's the ammonium. And since it's positively charged, it's actually going to take the place of like a metal in the ionic compound. And then we have hydroxide right here, which is a base, right? And its formula is OH minus. It's just hydroxide, nothing else, just one of those that you have to remember. And then the other thing to note too is that when you add an extra H to things, for example here, we had carbonate here, which is CO3 minus 2, right? Well, just below it we have HCO3 minus 1, and that becomes bicarbonate, right? So 2 things happen when you add an H or a hydrogen to a polyatomic ion. It adds on the face of it, it adds the name bicarbonate in front of it, right? Instead of just being carbonate, it becomes bicarbonate. But then also, since it gained a hydrogen, which usually has a plus charge, right? The 2 minus here, right, on the carbonate became a 1 minus on the bicarbonate, right? We have that happening here also with the sulfate. So this is instead of it being a carbon in the carbonate, it's sulfur this time, and we added an H to the sulfate ion, and it becomes hydrogen sulfate or bisulfate, right? And notice that it went from having a 2 charge there to a 1 charge there after you added the hydrogen. Let me erase that, it's kind of hard to see. Try that again. Yeah, so here's the 2 charge here. Alright, and when you added the hydrogen to it, it became bisulfate, or hydrogen sulfate, and it became a -1 charge. Right? -1 charge. So let's just do a really quick example of how to name a polyatomic and write its formula. I guess my favorite one these days is magnesium. So we'll do magnesium again, which again has a +2 charge, right? And I want to make something like magnesium nitrate, right? Which has a -1 charge. So how do I make it so that this is a balanced formula, where the anion balances out the charge of the cation and vice versa, right? Well, if this is a -1 charge, then I need 2 of these right here, right? If nitrate is a -1 charge, then I need 2 of these to balance out a +2 charge of magnesium. So the way I would write that is magnesium, and I would put parentheses, and O3, right? And then I would put 2 there, because it's 2 of them. Right? And so that then becomes the name magnesium nitrate. Magnesium nitrate. So it's simple as that. Yeah, so naming ionic compounds is a little bit confusing. It's just going to take a lot of practice. And one of the things that you're going to have to do is memorize all these polyatomic ions. Right? I won't give you that on a test. When you do naming of compounds and stuff, I'm not going to give you that on the test. So you have to memorize the polyatomic ions, and it would be good to. You don't even have to memorize, any of the charges and stuff of the normal ions and the normal cations and anions over here in the periodic table, because its valence number and its charge can be deduced just from its position on the periodic table, right? Which we went over before. So ionic compounds were a little bit confusing to name and write their formulas of, but next is the covalent compounds, and those are much easier. So just a quick review here. What are covalent compounds? Well, they are molecular compounds that are formed between 2 nonmetals, and they share electrons, like we were saying before. And they share these electrons so that they can have a full outer shell to achieve stability, right? And we already knew that. So let's move on to naming these covalent compounds. Super simple. You name covalent compounds or molecular compounds rather. I'm sorry, and their formulas based on the number of each atom or element that it's in, right? So if there's 1 of it, it's mono. If it's 2, it's di. If there's 3, there's tri. 4, tetra. 5, penta. 6, hexa. 7, hepta. 8, octa. 9, nona. And then 10, deca, right? And that prefix that distinguishes the number of each element, right, goes on both the nonmetals that are in the compound. So quite literally then, if we have something like this, CO2, which is carbon dioxide, there's only one carbon, which mono is one, but if there's only one, that's kind of understood that if you don't have a prefix on there, it's understood it's one. So you don't have to actually put a mono there, but there are two oxygens, right? So that's why it's dioxide. Same thing again with uh, carbon disulfide, right? One carbon, so you don't have to have a prefix there. But there's two sulfurs, so we call that disulfide, right? Here's the first one we have that will have a prefix on the first one, first element involved. Um, Dinitrogen, right, for two nitrogens, and then a single oxygen, so it's oxide. Both of these right here, there's only one of each, right? So it's simply nitrogen oxide, right? So the uh, the second element involved always still has the "ide" at the end, right? But it's really easy to name them because you just use the Greek prefix for each of the numbers. So sulfur here, there's one of them, so it's just sulfur, and there's six fluorides, so sulfur hexafluoride, and then one sulfur there, three oxygens there, sulfur trioxide. So the nonmetals or the molecular formulas are much more simple to name. They'll get a little more complicated later on when we talk about organic formulas and compounds, but for now, that's all you really need to know. And then these are just common commercial uses for each one of these compounds. You can look at those later. Just trying to bring a little bit of realism to the class. So the next slide is just a handy dandy flow chart that helps you name compounds, both ionic and molecular, right? So let's go down the flow chart and go over to ionic, right? Ionic is always between a metal and a nonmetal, right? And the metal, or ammonium, is always known as the cation, right? Because it's always positively charged, right? And then the nonmetal is known as the anion, right? And these are the ones that are negatively charged, right? Negatively charged, right? And these can be either monatomic, which is just a single ion, or polyatomic, which are those other ones that were in that big chart, right? Like sulfate, nitrate, nitrite, right? So if it forms only one positive ion, right? Then you can just use the name of the metal or ammonium, right, as the beginning of the name of the ionic formula or ionic compound. But if it has more than one positive ion, for example, iron, which had iron 2 and iron 3, you'll have to use the element, right, followed by a Roman numeral, which I showed you that, to get an equal charge, right? And then as for the anion side, if it's monatomic, which means it only has one ion, you just use the first syllable and follow it with "ide." If it's polyatomic, you have to use the name of the polyatomic ion, which is the reason why I told you have to memorize those polyatomic ions. And then for the molecular compounds, right, it's always two nonmetals. The first nonmetal, you just use its name with the Greek prefix that tells you how many there are. And then with the second nonmetal, it ends in "ide," right? But again, with that one, you also use the Greek prefix to tell you how many there are. So, as you can see, then naming molecular compounds are much simpler than ionic compounds. So that brings us to talking about then, after discussing so much about naming them, let's talk about their structures now. So Lewis structures are used very commonly in chemistry to demonstrate the structure or the bonding structure of molecules, right? Of molecules. So these are some formal things that you need to know. That might be definitions on your exam that you might need to identify, right? So a molecule is represented by a Lewis structure in which the valence electrons of all the atoms are arranged in to give octets. So recall I said octets, right? That's 8 electrons in its outer shell, in the valence shell, right? The only exception for that is hydrogen, which only has 2 electrons, so it doesn't have to, it doesn't fit anywhere. Anything. So basically, we're trying to each atom here that's sharing electrons is trying to achieve a noble gas arrangement, which basically means again a full outer shell. And just as a reminder, we were talking about before neon, right, which has 10 electrons. So if we had neon, 2 electrons are in the first shell, and then it has 8 electrons in its valence shell or its outer shell. So if you wanted to draw the Lewis structure of neon just by itself, you wouldn't have to draw any other atoms combining with it because it has already achieved noble gas arrangement because it has a full outer electron shell, and so that's why you don't have to draw anything else with it. So other elements though have to, other atoms though have to combine with other elements so that they can make compounds, so they can achieve the same thing that neon has just by its existence, right? The shared electrons or bonding pairs are shown as 2 dots or a single line between atoms. So you can see here we have a bond between carbon and hydrogen right here, right? And it is shown as either 2 dots or a line, right? And then non-bonding pairs of electrons, or also known as lone pairs, right, are just outside. So, for example, in this nitrogen here, there are two lone pairs right there, or non-bonding pairs of electrons. And then in oxygen, there are 2 sets actually of non-bonding electrons, right there and right there. Right? So it's much easier to see on the ones that have the lines to represent bonds, because then the lone pairs really do look alone, right? And so this is methane, right? And methane has 4 hydrogens around it, because recall from the periodic table that carbon has a charge of -4, meaning that it can accept 4 electrons, right? And then hydrogen has charges of +1. So you need 4 hydrogens to balance out 1 carbon, and that's why carbon has 4 bonds to 4 hydrogens there. If you recall, nitrogen is a -3 charge, right? -3 charge. And so same thing with these hydrogens, there's +1 charges all around. And you need 3 of those +1s to balance out the -3 of a nitrogen, right? And the nitrogen has a lone pair that's already together. And then oxygen here is a -2, so it only needs 2 hydrogens of +1 charge to become a balanced molecule, right? Balanced molecule. Just as an aside, let me clear this real quick. The ammonium ion, so this is ammonia, as is, it's called ammonia, right? But if I add an extra proton here, or hydrogen, right? Let me clear that, try that again. But if I add another hydrogen here, right? remember that the hydrogen has a +1 charge. This used to be ammonia, and ammonia was neutral, right? But now it's become ammonium after I added that extra hydrogen, right? And so now its formula is NH4 plus. Should be very familiar to you because this is the ammonium ion that was on the polyatomic ions list, right? That's how you make an ammonium from an ammonia. You add a proton to it or a hydrogen, right? A proton. By the way, when I say proton, that's because a hydrogen has 1 proton, right? So that's what I mean. 1 plus charge, proton. Anyway, so let's talk about some special molecules known as diatomic molecules, and they are just molecules of 2 of the same element bound together in a covalent bond, right? So let's talk about now electronegativity and bond polarity. So this wasn't so important when we were talking about ionic compounds because ionic compounds have a complete transfer of electrons. So when that metal transfers an electron to the nonmetal, it becomes positive because it lost a negative charge, right? But since that nonmetal then gained an electron, it becomes negative because it gained an electron. So when you look at an ionic compound, one side, the metal, is always positive, right? Is completely positive. The other side of that ionic compound, the nonmetal, right, is negative. So when you think of, for an example, a sodium chloride, the sodium is positive and the chlorine is negative, right? And so we don't have to really worry about if there's any partial charges there, right? But when we talk about covalently bonded molecules or molecular compounds, since they're covalently bonded, they're actually sharing electrons. They're not transferring those electrons. So when that happens, then there's different degrees of negativity or positivity throughout the molecule. And so that's what we talk about. That's what we're talking about when we're talking about bond polarity. And then bond polarity is also affected by electronegativity, right? So first, let's take an example of a nonpolar molecule, and that nonpolar molecule is hydrogen gas, right? H2. Hydrogen gas, or H2, has an equal sharing of electrons because they're the same atom, right? And they're both sharing the electrons right here, right, and nowhere else. So it's nonpolar because there's not a concentration of charge in any direction, and they're being shared between negative charge, and they're being shared between both hydrogen atoms equally. But then you take an example like HCl, which is either hydrogen chloride gas or hydrochloric acid, right? HCl. We have a hydrogen here, right? And we have a chlorine here. And when they bind with each other, most of the electrons are over on the chlorine side because hydrogen doesn't have a lot of electrons, right? The only electrons it really has are the ones it's sharing right there with chlorine in the middle. But chlorine has all these other electrons that are lone pairs out here, right? So what that means then is that on the hydrogen side, it's partially positive. But on the chlorine side, it's partially negative, right? And so that's what we mean by bond polarity. There's there's poles, right? There's bond polarity. And then, so how does electronegativity play into it? Well, electronegativity is an atom's affinity for electrons. It likes to draw electrons, or it likes to have a lot of electrons, right? So as you move across the periodic table to the right and up the periodic table, the electronegativity, or the atom's affinity for electrons, increases, right? And so the most electronegative atoms there are oxygen and fluorine. We'll talk about oxygen's electronegativity a lot, especially when we go to organic chemistry, right? But they have very high numbers when it comes to electronegativity, which means that they're going to draw a lot of electrons towards them, meaning that whatever side of the molecule they're on, it will be mostly negative, right? So here is a easy chart to kind of summarize what I just said. If you have an ionic bond, like I was saying before, right, the electrons are transferred. And so you have a full positive on that side, full negative on that side, and there's no varying degree, right? And the electronegativity difference here, right, is quite large, right? So, but if you have a polar covalent compound, right, which means it's a molecular compound covalently bonded, but it's polar, right? One side is partially positive and the other side is partially negative. Why? Because the electrons are unequally shared, right? And that's a good example of that is the hydrogen chloride example I just gave. And then we have nonpolar covalent bonds where the electrons are equally shared, right? And a very good example of that is the hydrogen gas that we just talked about, right? This is also known as a dipole, by the way. When you have a partially positive on one side and a partially negative on the other side, that's also known as a dipole for two poles. And just to reiterate something that you need to remember, there are two types of covalent bonds, which you just talked about here, right? We have the nonpolar covalent bond, and then we have the polar covalent bond. Right? You remember which is which? Yes, you do, right? The one that has the partial charges is the polar one. The one that is equally distributed electrons, shared electrons, with no partial charges, is the nonpolar one. So just remember that. Let's see here. So that takes us to talking about the VSEPR theory. Okay, so the VSEPR theory has everything to do with the shape of molecules, right? So again, whenever I have actual definitions like this in words out for you, it means it's important, right? So VSEPR stands for valence shell electron pair repulsion theory. And the gist of it is that electron pairs like to repulse each other or be as far away as possible from each other, right? Which is stated here in the second line, far apart as possible, okay? We already know the first one here because it says around a central atom, and you saw that when I did the carbon dioxide example. And then they're attached to the shape is determined by the number of atoms that are attached to the central atom, right? So the biggest thing here is that VSEPR theory is all about electrons being as far away as possible from each other when they bind or when they form bonds, right? When they form covalent bonds. That's the biggest thing. Just, remember that. Okay, so now let's do some examples to demonstrate VSEPR theory, right? You saw me do the example of carbon dioxide earlier with the Lewis structure, right? And it looks something like this. And I just, by habit, because I'm a chemist, I put the electrons, the lone pairs for the electrons of the oxygen like this, right? And the reason why I did that is because VSEPR theory says that the electrons want to be the electron pairs want to be as far away from each other as possible. So that, along with how they're bound to the central atom, right? How the atoms are bound to the central atom, dictates what shape carbon dioxide is going to be. So this is actually a very accurately drawn Lewis structure, and so we call carbon dioxide to be in the linear electron group, right? The linear electron group makes sense because it's just a straight line, linear. And when we draw its 3D structure out, which is very similar to its Lewis structure just without the lone pairs, we see that the bond angle between the two oxygens and the carbon is 180 degrees. 180 degrees, right? So it has a linear shape as well, right? So carbon dioxide was pretty simple because we had already done that on the previous slide as an example. Let's try doing a central atom with 3 electron groups, right? 3 electron groups. So a good example of this would be formaldehyde. So the structure for formaldehyde looks like this. It's a carbon and has an oxygen at the top with a double bond and 2 hydrogens, right? And that's its Lewis structure. That's its Lewis structure. But since its Lewis structures has the bonds mostly at 90 degrees, right? That's not following VSEPR theory. So I want to follow VSEPR theory. I want to get these electron groups right here, right? The single bonds, these 2 single bonds right here, these electron groups, as far away from this double bond group of electrons as possible to follow VSEPR theory, because VSEPR theory says electron groups are trying to be as far away from each other as possible. So to do that, I bend the angle a little bit and I achieve the furthest distance I can with those electron groups without them hitting each other on the bottom side, right? So for formaldehyde, this is a trigonal planar. Trigonal planar electron group. And then again, if I draw its structure without the electrons, just as a ball and stick model, like so, I can see here that this angle is 120 degrees. So it's also trigonal planar in shape. Pretty simple so far, right? Pretty simple. Let's move on to the next one. So now let's try drawing a central atom with 3 electron groups in which the 3 electron groups are not all bonds like they were in formaldehyde. So silicon dioxide, very simple, right? Because using our molecular compounds naming convention, there's only one silicon because there's no prefix, and then the di means 2 and oxide means oxygen. That means silicon dioxide, SO2, like so. We'll start out by drawing its Lewis structure like this, right? And we can count up the number of valence electrons and fill in the spots like so. I'm not going to do that here because this is just about the shape. All right. Everybody has their octet. This oxygen has an octet, right? This sulfur has an octet, 2, right? 2 from this bond, 4 from this double bond, and 2 from the lone pair, right? That makes 8, so that's the full octet. And then oxygen with a full octet, which you already know from carbon dioxide. So, but I didn't follow VSEPR. This is just a Lewis drawing, right? But VSEPR, if I want to if I want to follow VSEPR, I need to get all these electron groups away from each other as much as possible. So it's going to look like this. Sulfur still has its 2 lone pairs at the top, but now I'm going to bend them down for the bonds. I'm going to bend down. Sorry, those oxygens, electrons are kind of messy. But there are 3 lone pairs down there. And draw my double bond down. And it has 2 lone pairs, right? So again, this is a trigonal planar electron group. trigonoplanar electron group, right? But when I draw its, the difference here though is when I draw its ball and stick, like so, and since it doesn't show any lone pairs on it, right, it's not trigonoplanar shape. It's actually a bent shape. And the bond angle here is still 120 degrees, right? 120 degrees. Let's try another one. So now let's try drawing a central atom with 4 electron groups, right? So here we have methane, which you saw the Lewis structure for methane earlier in the presentation, lecture. It looks like that, right? The problem though is that this Lewis structure doesn't really follow VSEPR, right? Because even though on paper this guy looks like it's pretty spread apart with its electron groups here, they're not, because remember that molecules are three-dimensional, and so those those electron groups or those bonds can actually bend out of the paper in front and behind the paper to give it as much room as possible, right? So how do I do that? Well, let's start out by drawing its ball and stick structure. There's my carbon in the center, right? I'll start out by drawing my hydrogen up here, okay? And I'll draw my other hydrogen there, my other hydrogen here, and this hydrogen is coming out of the paper, okay? If I connect that there, and that there, that there, and that there, and those here, right? Now they're as far apart as possible and they follow VSEPR theory, right? This is known as a tetrahedral electron group. It's a tetrahedral electron group. And it's also a tetrahedral shape. Right? And it's important to note that the angle here between these bonds is 109 degrees. Right? 109 degrees. There's an easier way to draw this so that you don't have to be an expert at drawing 3D molecules. Most chemists will just draw it this way, where they have C in the center, right? The hydrogen that's going up will just be the same as it was in the Lewis structure, but then this hydrogen will bend down a little bit over here, and then when you have a wedge that looks like this, that means that the hydrogen is coming out of the page, right? And then when you have a dashed wedge like this, that means that the hydrogen is going behind the page, right? So this one with the solid wedge, it's coming towards you, and this one with the dashed wedge, it's going towards the back of the paper, right? This is known as the wedge dash notation. Right? The wedge dash notation. So if you don't think you can draw this, draw that instead. Okay? Let's try another one of these atoms, central atoms with 4 electron groups. Now we're going to do ammonia, and you remember ammonia from the previous slides, right? Let's draw its Lewis structure first. NH3, right? With a lone pair at the top. Are we following the VSEPR theory here? No, they're pretty close to each other. So again, this is one of those times when you're going to have to draw just for demonstration purposes here, a ball and stick in 3D. We'll start out with our nitrogen right there, right? And there's a lone pair up here, right? And then I'll have my hydrogens come out like this, right? And again, I'll make a shape out of this, like that. So again, that looks just like the one for methane, right? So that is actually a tetrahedral electron group. Right? And again, very important to note that this angle right here is 109 degrees. Okay? Very important to note. But when we draw the ball and stick figure, you have to remember that the top here is actually a lone pair. So it doesn't form a tetrahedral shape. It's actually a trigonal pyramid. Or some people just call it trigonal pyramidal, right? Because the pyramid is just there, right? If you had a bond up here going to something, then it would be a tetrahedral, but since it doesn't have that, that's why it's a trigonal pyramidal, or trigonal bipyramid. Sorry, trigonal pyramid. And again, remember, 109 degrees between these bonds. And then to draw the wedge dash diagram, nitrogen in the center at the top, solid wedge here means that the hydrogen is coming out towards you, dash wedge over here means it's going into the paper, and then a solid line over here means that it is flat with the paper. Alright? And we have one more central atom with 4 electron groups to try. And that's water. Let's draw water's Lewis structure. Pretty simple there, right? Pretty simple. One of my electron pairs is a little off. Sorry about that. It should be a little closer to the oxygen, right? But just notice though that the reason why this is even different from the other two, is because we have 2 lone pairs here. Right, we have 2 lone pairs. The nitrogen had 1 lone pair in the previous slide, and the one before that with the methane had 0 lone pairs, right? So we're going to get a different shape again. So let's draw this so that it obeys Vesper theory, right? We'll do this by having our oxygen right there, and then same thing as before. This time there's a hydrogen there, and there's a hydrogen there, and then there's a lone pair over here, and a lone pair over here, right? So if I connect the lines, between all the lone pairs and the hydrogens, right? I make another tetrahedral. These are lone pairs right here. I know you can't see them, so maybe I should make them darker. There we go. We make another tetrahedral electron group, right? But if I just draw the ball and stick without the electrons, the electron group, lone pairs, right? I don't have anything to draw a tetrahedral with anymore, so this is just a bent shape. That's just a bent shape. And then just also, again, very important, this bond here, the bond angle, is 109 degrees. And draw a wedge and dash diagram here. Dash means the hydrogen is going behind us, or behind the piece of paper, and a solid wedge means that the hydrogen is coming out towards us, right? So just remember that there is a difference between the electron group and the shape, right? They're not always going to be the same. The electron group and the shape. Go rewind if you need to see the differences again. And I think there's a chart in your book that gives you a summary of it all too. So to end this lecture then, let's talk about some intermolecular forces. Yes. Let's talk about some intermolecular forces, right? Intermolecular forces. Intermolecular forces are what they sound like, what they are, right? They're the forces that occur between molecules. By the way, if you didn't know that, inter is the prefix for between from Greek, in Greek. Right? So what that means is that the forces between molecules. There's also intra, which means inside in Greek. So like for example, intravenous, right? Like an IV, that's inside the vein, right? Intra. But we're talking about inter here, which is between, right? Between. So let's start talking about these different forces, right? Anionic bonds, of course, we've already talked about this before. Just a quick little review. They're not; those aren't really intermolecular forces, but the forces of attraction happen in their arrangement, such as that, right? And then the example is sodium chloride, and the strength of an ionic bond is actually very, very strong. Same with a covalent bond here. Two nonmetals, right? Good example of that is two chlorines put together, also very strong. So they just have these two here to give you a perspective or context into how strong each of these intermolecular forces are as compared to actual bonds. So don't confuse the two. Don't confuse a bond as with an intermolecular force, right? Don't confuse the bond with an intermolecular force. So the first one to talk about is a hydrogen bond. Hydrogen bonds are actually very important. They're the ones that compose your DNA, right? They keep your DNA zipped together. If you remember, a DNA molecule is a double helix with a sugar phosphate backbones, and on either side, and then in between are nitrogenous bases. And the thing that holds those nitrogenous bases together are hydrogen bonds. So they're very important, right? When you're doing DNA replication or transcription rather, those hydrogen bonds have to be broken with a special enzyme, which we'll talk about later. But those hydrogen bonds are what holds your DNA together, right? So what exactly is a hydrogen bond then? We'll use water as an example, right? So if I draw a water molecule like I would using Vesper theory, right? There's one there's one water molecule right there, right? And it has remember, a partial, whoops, hold on. I can't draw my partial sign. There we go. Does that work? There we go. Partial negative on the oxygen side, because oxygen is super electronegative, right? And on the hydrogen side, right here, it has a partial positive. Partial positive. When that comes in contact, when that molecule comes in contact or comes close to another water molecule, maybe I can just draw that water molecule. There we go. Draw another water molecule there, right? Since this is a partially positive hydrogen right here, and this water molecule, since we have a partially positive hydrogen there from the first water molecule, and the second water molecule is composed of the same exact thing, we have a partially negative oxygen there, right? And a partially positive hydrogen there. This partial positive hydrogen from the first one is attracted to the partial negative of the oxygen on the second water molecule, right? And this is known as a hydrogen bond. I put H here because sometimes people just call it H bonds, right? So hydrogen or H bonds, right? So interestingly, right? How much energy do you think is required to actually break a hydrogen bond? I'll give you a hint. You break hydrogen bonds when you boil things. That's why they become gas. That's why the water is no longer liquid. So it's approximately 100 degrees Celsius. That's why you're able to boil water, right? Boil water. So that's known as a hydrogen bond, right? And it's usually, again, between a hydrogen and that's partially positive and electronegative nonmetal, right? So that can be a nitrogen, a fluorine, or even an oxygen like we did here, right? So those are hydrogen bonds. Hydrogen bonds, cool. All right. So next, let's talk about dipole-dipole interactions, right? So dipole-dipole interactions are just interactions between uh, two nonmetals that have dipoles, right? Two nonmetals that have dipoles, or two nonmetals that have partially positives on one side and partially positives on the other side, right? So an example of this could be, for example, the HCl that we talked about earlier, hydrogen chloride, or hydrochloric acid. Like that, right? And then here's another HCl. Two molecules of HCl, right? Partial positive for the hydrogen, partial negative for the chlorine. Same here, partial positive for the hydrogen, and then partial positive negative for the chlorine, right? And this chlorine here being attracted to this hydrogen here that's partially positive, that is a dipole interaction. Excuse me. Hydrogen bonding is far more strong than dipole interactions, right? That's why I put this at the top. These hydrogen bonds are way more strong. Dipole interactions are not as strong, okay? And then the weakest of all these are called dispersion forces. We'll hear a lot about that later. For example, like London dispersion forces. We'll talk about that later, though, right? So how do we do dispersion forces? They're the weakest of them all, and basically it's like this. Okay, so say I have an atom there, right? And not an atom, but a molecule there. Sorry, a molecule there, and I have another molecule here, right? And I have a nucleus of the molecule here, and I have from the first molecule, and I have some electrons, right? And then over here, though, I have a nucleus over here from a molecule, and electrons over here. So what's happening is that we get a partial charge, right, in these molecules because the electrons from the first one over here, right, are dispersing the electrons from the second one, exposing this nucleus right here, giving that nucleus a partial positive charge, right? And then giving this molecule this side, that was supposed to be a partial symbol. Let me try that again. There we go. A partial negative charge, right? So the nucleus, remember, nuclei are positively charged, electrons are negatively charged, and when they come close to each other with another molecule, the electrons from one molecule can make the electrons of another molecule disperse to the other side. And when it disperses to the other side, it exposes the nuclei to be partial positive on one side, and then the electrons are all gathered on the other side, making it partial negative on the other side, right? So what happens then is that what happens then is that the result is this. And I'm going to shut myself off for a second here so you can actually see what I'm drawing, right? Now, these dispersion forces cause it so that the nucleus is on one side, and we have electrons here, and nucleus on the other side, electrons here, like that, right? And so now we have two sets of nuclei and electrons that have become partially positive and partially negative. So that's partially positive, partially negative, partially positive, and then partially negative. Alright? And this all happened because the electrons from the first guy over here, the first set over here, dispersed the electrons from the second set over here, moving them over to the right side. Right? And then that left the nucleus of the second one exposed. Then it attracted the electrons from the first one to this side. So that's why you end up with something that looks like this. So now we have temporary dipoles formed. These are very temporary, but they're temporary dipoles. Right? And then there's a little bit of attraction that's in between there. That is a dispersion force. Very small. Let me write that again. Dispersion force. Yeah, dispersion force. That is a dispersion force, right? And again, those are the weakest of them all, right? Those are the weakest of them all. Okay, so I think that ends this particular lecture. Let's see. Yes, it does. So I already said this on the last lecture, on lecture 2, but again, by the end of the day today, which is February 2nd, 2021, your Blackboard assignments and quiz covering lecture 1 are due. So make sure you get those in before the end of the day today. And by the end of the day, I mean like 11:59 p.m., okay? And then next week on Tuesday, your Blackboard assignment 1 and 2, Blackboard assignment 2 and 3 are going to be due, okay? And they're going to be due, and then also the quiz for 2 and 3 are going to be due at the same time, 11:59 at the end of the day on Tuesday. So remember that. Good luck, and I'll see you at the next lecture. I have office hours today at 4 to 5 if you want to come talk to me on Teams. If you don't know how to use Teams, you should already have Teams installed on your computer. If not, you can download it from Microsoft. And all you have to do is log on to Teams using your TCCD email address. So as long as you have that, you can log on using that, and we can talk on Teams. You should already be added as a member of my team, of my class. And so, again, my office hours are from 4 to 5 on Tuesdays and on Thursdays too, and other days too if you want to make an appointment. And then also remember that not this Thursday, but next Thursday will be our first exam. So we'll have one lecture for Tuesday, and then the exam will be on Thursday. The stuff that will be assigned as homework and a quiz on Tuesday will still be due the Tuesday after, like normal, but you will still have your exam on Thursday. Okay? Any questions? Let me know. You guys have a good day.